in real time, then communication also in real time, then control, decision making, and there are few constraints. The constraints which you have to follow, one of the major constant is the time constant, which so you call it real time. Real time means time defined by an external object. That means if this is your system, this system has to respond to the stimuli from external world. This is an external world, external input. So it should react and give some output. So this the delay between time delay, suppose this external impulse comes at x of t and this output goes at x yt minus tau. This tau has to be within a between 0 and some maximum time constant. That means to the stimuli xt, external stimuli, you are generating an output. Example is, let us say, anti-lock braking systems. Anti-lock braking system. This anti-lock braking system is generally in the car. What happens there? Whenever there is a skid between two wheels, if there is one wheel, there is another wheel. If there is a unequal torque in both the wheels of the car, then immediately there is sensor activated and there is a particular braking mechanism which is comes into phrase so that there is no skid. So whenever there is such a sensor mismatch here, the anti-lock braking system output is here, there should be a limited time delay. Otherwise, the passenger will meet with an accident. So there is a real time or time constraint. That is one of the most important facts about embedded system. Then what else? So there is a second is memory constraint. Memory. That means you have to work on limited memory. A computing system, when it is working, remember all computing system which processes signal is associated with the memory. A memory and arithmetic logic unit. These are the prime things. Okay, so therefore the memory is also limited. You cannot have infinite memory. Just like your laptop where you can have few terabytes or gigabytes of memory, primary RAM, and few terabytes of secondary RAM. But in case of embedded system, the memory will be limited to few kilobytes, 8 kilobytes, 16 kilobytes, something like that. So there is a limit of the memory. So that means the signal which you are handling in through this XT, it has to come to the system. System has a memory. In the memory, it has to reside, and the code has to run in the memory, and output has to be generated. So this memory is limited. So second, constant number one. This is constant number two. What is the third constant? Third constant is power. Most of these embedded systems are they run on batteries. So you cannot have infinite number of battery. You have just simple limited battery pack, which may be. So a battery pack is generally how it is specified. A battery pack, Mesram, any idea? How the battery pack is specified? Can anyone tell me? You have a battery pack, Abhijit Nandan.
Should I tell, sir?
Yeah, Abhijit
Yeah,
Nandan.
Abhijit Nandan.
Abhijit Nandan.
Abhijit Nandan.
Abhijit Nandan is not there, so I'm removing. Okay, Abhisar Das. Abhisar Das. Vishwasri Roy.
Yes, sir.
Hmm. Can you tell me how do I specify a battery pack? If possible, switch on the video. Otherwise, okay. Vishwasri, any idea how to specify a battery? It is specified in terms of ampere hours. when I tell you about ampere hours or milliampere hours, then sometimes it is also specified with respect to per kg or per liter, something like that. It is called specific battery capacity. So that means that this is limited. You cannot have many ampere hours. You have limited ampere hours and the weight is also very less. So therefore, the third constant is power. So you can say time, space and power, these are the three things which deals with the constraints on the embedded platform. So now you must be wondering then, how do I design a system and what are the components of the embedded system? What are the components? So if I say about components, I have already told in the last class, one of the major components of this embedded system is a processor. A processor which is as efficient as. So there are thousands of processors nowadays. If you go to the market, in 1970s there are only one microprocessor, but as progress there are so many microprocessors, depends upon different kind of architecture like CISC architecture, RISC architecture, ARM architecture, Harvard architecture. So these are different architectures which has been. So the processor is one of the major components of the embedded system. Then apart from the processors, there are peripherals. Like mixed signals, ICs, communication modules. Then actuators and sensors. Then we'll have battery, then RF circuits, like this, lot of things. So can you guys tell me what is a mixed signal circuit? Manidip Bade? Manidip?
Yes, sir.
Tell me one mixed signal circuit. Manidip?
Yes, sir. I'm here.
Mixed signal means what? Both digital and analog together. So tell me one IC which is both digital and analog together. AD converters, modulators, demodulators, digital modulators. Okay,
Yes.
PWM. Okay, PLLs, phase lock loops, voltage to voltage to voltage control oscillators, VCOs. So these are mixed signal circuits.
Yes.
Then you have actuator sensors. Can you name one actuator? Last time I told you to do some homework. Actuator in your cell phone. Tell me one actuator.
Actuator in mobile phone, sir.
Yes. Tell me one. You have actuators in your cell phone. Lots of actuators. Vibrator is an actuator. Speaker is an actuator. Yeah. So these are lots of actuators you can see. Right.
Yes.
So, so did you guys Bethapudi Dibya Sudha? So did you see the sensors of a cell phone? So can you tell me one specific sensor which is very modern? Bethapudi Dibya Sudha. Why Bethapudi?
Yes, sir.
Tell me one modern sensor in a cell phone.
Hello?
A modern sensor in a cell phone.
Screen sensors, GPS, proximity sensors, weather sensor.
This sensor which I wrote, what is that sensor? What is written in my screen? What did I write just now on the screen? Can you see my screen? What is that?
Yes, sir.
What is written here? LiDAR.
Battery.
LiDAR here. You can see. What is a LiDAR sensor? So it is laser detection. That means you can use it for virtual reality and measuring the depth. So all of you find out what is this LiDAR sensor. iPhones have it, and you can have an external sensor on the cell phone. Okay, please do it. LiDAR sensor on the homework which you have submitted, you can add this LiDAR sensor. So what I mean to say is, so
Okay.
that means there are a lot of things which come together to make one ES. So for example, there is high frequency circuit, low frequency circuit in your cell phone itself. Your high frequency is, what is the cell phone frequency generally? Mohit, CH Mohit, tell me one cell phone reception frequency. It is between 4 gigahertz to 5 gigahertz. Okay, so this is very high frequency. Okay, and what this frequency which you speak is what frequency? Is baseband, that is your speech frequency. So there is high frequency and low frequency together. That is one more thing, hybrid. Then there is digital and analog together. Digital as well as analog and hybrid circuits, all are together. In your cell phone,
speech frequency means my voice frequency.
Yeah, your voice frequency is low and the transmission frequency is very high. Cell phone, that CDMA frequency. So there are 5G, 4G, those frequencies are very high. This has to be modulated. Otherwise you cannot. So then there is digital and analog and mixed signal. All are together. For example, you are speaking to a mic. There is a mic. So this mic receives, it is an analog signal. Then it converted into digital. Then digital, there is some kind of coding, etc. Then again, when you are listening, it is again analog. So digital and analog together. Then there is high voltage and low voltage and medium voltage. All are there together. Your voltage could be plus minus 12 volt. Your low voltage could be plus minus 2 volts. Okay, medium voltage may be plus minus 5 volt. So these are the different voltage levels in a typical embedded system. So there is multi-level power supply. Then D is sensors and actuators together. For example, you can have speaker, which is an actuator, mic, there is a sensor, there is a vibrator, there is so on and so forth, different kinds of sensors and actuators together. So all these things are, so these are some of the very opposite things, which to package it is a very difficult thing. So packaging is a formidable task. A typical embedded system, the main thing is spent in packaging. And it is an art, it is art. So when you package high frequency and low frequency signal together, digital to analog together, there is a lot of interference issues. When an analog circuit and a digital circuit resides on the same PCB, what is the problem? Hasanul Haq, what is the problem? Hasanul? Hasanul, are you there? If you are not attending, no problem, but don't become a mute thing, you know, that creates a very bad impression. Hasanul, are you there? Not there. Okay. Yadubansi Krishna. Actually, Pooja, whomever I am telling they are not responding, please make a mark. If this is repeated, then we have to take some action. Because there are some serious learners, even though there is online class, I know there are certain students who are really serious about learning this subject. So we should not have people who are very casual. Let them not attend the classes. We will pass them, no problem. But they are not interested to learn, so we cannot make them learn. No punishment, nothing. But just to maintain the dignity of the class, those who are not responding, they should be removed from the class. Pooja, please make it a point. I have removed 2 people, so please note down their names. Then Kadasi Namrata, can you tell me what is the problem if I put low frequency and high frequency circuits together?
The interference.
Yeah, interference. That means if there is a circuit here, let's say there is a current which is flowing here. Generally, all are current controlled. So suppose there is a very high frequency current flowing in this loop, and there is another loop here. So if this frequency is, so the flux linkage is there, therefore this will interfere with this. So there will be interference. High frequency and low frequency interfere together. Thank you. So what about digital circuit and analog circuit if they are together? Anantaraj, can you answer this? If I digital circuit and analog circuit I put together, what is the problem? Anantaraj.
Yes, sir.
Huh.
So, so I have to think about it. So I cannot think right now.
The digital circuits are switching circuits. Suppose I have a digital 5-volt supply and digital ground. Make it simple. So this is connected to one digital circuit. Let's say this is digital IC chip, digital chip, and same circuit. Suppose you connect to an analog chip. You'll find this current. If you observe the current here, so what happens to this current? This current, because of the switching, digital circuits are basically switching circuits. So the current here will be drawn like a spikes. Whenever there is a switching, lot of current. So this spike current, because of this finite inductance, this will disturb this voltage. Therefore, digital and analog should be decoupled either by capacitors, decoupling capacitors, very powerful, or they should have separate ground and separate supply. Because this jumping, this current spikes will create a voltage swing here. So because these digital circuits, for example, an inverter circuit, digital inverter, MOS inverter looks like this. So this is resistance. So whenever this is switching in, the current will, there is a spike of current. So this spike of current, when it passes from the power source, there will be, this voltage gets disturbed because of the finite inductance, which will interference with the analog circuit. And digital circuit, they work in two levels. Like if it is TTL logic, 1 is 0 to 1 volt is 0, maybe 4 to 5 volt is 1. But analog circuits are continuous. So any disturbance in digital will create disturbance analog. So they should be separated. So digital analog putting together, binding together is a very formidable task. You have to have proper sense filters, etc. They should be separate. Is it clear? High frequency, low frequency, similar digital analog. Then there are multi-level voltages. If you look at a typical circuit, like a digital camera, I will show you next class. We'll have multiple voltage levels. A digital camera will have multiple voltage levels. Sorry about that. So I'll show you this digital camera sometimes. Okay, the internal architecture. For example, there is a flash light, and there is a communication RS-232. There is a communication IEEE communication port, and then there is some there is a movement of lens movement. So there is a motor. So all these different circuits, they have different power supplies. Similarly, a cell phone, if you look at, will have multiple power supplies. If you open up a cell phone, though we have one battery source, which is a lithium ion pack, but this battery source will go through a buck boost converter series. So these buck boost converters, they produce something called low dropout LDO outputs, different voltages. LDO, low dropout voltage regulators. LDO stands for low dropout. That means there is no dropout. The voltage doesn't fluctuate with current. So there will be multiple levels. So therefore, there will be multiple levels of power supply. So power supply design becomes a formidable task. Generally, for this kind of systems like embedded systems, the power supply requirement is like this. Voltage is low, but the current is high. Generally, whenever there are a lot of circuits, they come into play, there is a lot of capacitor, they get charged. So that demands a lot of current. So therefore, the voltage is low, but the current is high. So this kind of converter design is a very formidable task. So this is called a multi-level power supply with proper regulation. And of course, there is sensors and actuators. There are so many different kinds of sensors in a embedded platform. Temperature sensor, humidity sensor, current, voltage sensor, vibration sensor, so on and so forth. So there will be lots of sensors and perhaps some actuators, like there could be a heater, there could be a vibrator, there could be some kind of stepper motor, valve adjustment, etc., etc. So the challenge, you could realize that an embedded system design is a very challenging task, and it doesn't have any specific science, though there are lots of science integrated into it. But finally, you have to go by intuition. Intuition develops after doing lots of practice and developing the proper skill set. This particular course is designed to give you a lot of skill set. Once you are properly skilled, then you can design something. And once you design something, it will never fail. Like I am showing two cell phones. One cell phone here is an iPhone, which I designed long back, 5-6 years back, iPhone 10. This is an Android phone. This is from Motorola. This is from Apple. Okay. So I have several embedded systems. Like, you know, I have an embedded system here, which is AirPod. Then I've got an iPhone. Okay. There are lots of communication devices all around me. So what do you mean to say is that each of these devices have been designed and finally marketed. So embedded system design is primarily driven by what? Jangam Dinesh, if you want to design an embedded system, why you will design that? What is the primary motive? Design motive. Tell me. Jangam, tell me. Why you would like to design an embedded system? Why you want to learn this subject? Remember, the only one thing which drives embedded system design is money making, nothing else. Remember this. So that means I am coming to the economics of embedded system. There is nothing else which is the motivation of designing embedded system. For example, let me ask you this question. This is very sad, but this is true. Suppose somebody asks you to design a wheelchair, automated wheelchair, and somebody else asks you to design a different kind of, let's say, entertainment product, like a, you know, eye entertainment, which will have video, audio, virtual reality, everything on a glass. Which one will design? Gursimran Singh, which one you will design? There are two imitates here. One is to design a wheelchair. Two is designing a eye entertainment system, very advanced entertainment system.
Sir, wheelchair.
Why?
Sir, I think, sir, because in eye entertainment there is already too much competition, and I am not interested in doing that.
So your interest doesn't matter. So you will not design the health chair because you will not get money. Who will buy your health chair? But if you design a different kind of entertainment system, many people are going to buy it because here is the money. So remember, economics is very important. It goes beyond little bits of ethics. Embedded system is such a subject which is which people put more ideas, more energy into designing products which are not as useful as it should have been. Remember this. So if you design a medical device like wheelchair, it will undergo so many tests before it is recommended. By the time you will not make enough money because you need some, you know, some kind of funding to do this, and the funding will dry up and your marketing will not be possible. So it is a very difficult marketing. So this can be done as a social corporate responsibility, corporate CSR, corporate social responsibility by some money which will come. But this can be designed, developed, driven by self. That means this itself can generate lots of revenues for you. So remember, so this is called economics of embedded system. So this is called idea to market. If you have an idea about certain product, if you want to design using this embedded system, then you have to make, to go to market, there are lots of steps. Step number one, for example, is idea to prototype. So for example, idea, it goes to the prototype or lab prototype. You can say lab prototype. That means idea tested, then goes to commercial prototype. Then goes to manufacturing. So this idea to prototype, then IP generation, etc. comes over here. So here if the fund requirement is X, then this commercial prototype is 100X. Lab prototype to commercial prototype. Then here it becomes 1000 or maybe 10,000X. So if this is 10 lakhs to make the idea to work, then you need 100 into 10. That is 1000 lakhs or something like 1 crore, 10 crore to commercial prototype. Then maybe hundreds of crores for manufacturing. So who is going to fund you? So government can come in here, your institute, IIT, maybe your parents can come in here. 10 lakhs is not a big deal. But the moment you want to do commercialization, you need partners here. So these partners will come in only if they have money. Here, you know, all your ideas, ego stops here. Technology. After this technology, nobody gives a damn to you. People go for money people. So people with money are here. They may not be educated enough, but they understand business. So you have to present your idea to these people who are having money. Then these people will buy your technology or invest on your technology, provided they can make money. And then goes to manufacturing, which is big money. So this is called economic. So idea to market, the time gap is the economic. For example, say you are designing a different kind of cell phone. So if you are designing a different kind of cell phone, for example, it is just a wearable, like nothing else, or some kind of, you know, a ring or something, nobody, nothing else is coming. So it will have some kind of, you know, something will come here, I will press ring, so automatically everything is wearable. So this cell phone may not be, it's a new idea, but if you market it first, you are going to make lots of money. After that, even if your design is not that good, by that time you are already entered into the market and captured the market. So idea to market is one of the most important factors in embedded system economy. So whenever you choose a product to design, remember this first. So, so this is, so now let's go into how to tame, that means how to actually master this embedded system. So mastering embedded system is basically doing it. There is no time to learn about processors. The computer architecture course has become very outdated because nobody cares. Very few people who want to really design computer chips, they want to know architecture. But those who want to really make quick money, make quick products, then they don't have to worry about such things. They have to just pick up a processor which is very much there in the market and try to learn and make a prototype out of it. So that's what we are going to do. So we are going to learn a controller called Atmega 32 or Atmega controller, which is basically an 8-bit controller. We should learn it quick, maybe within this or 2 weeks time. So we'll know. So that means we are basically trying to know how to learn how to tame a processor, you can say, quickly. You have the basic idea of a processor that this should have a memory, this should have a arithmetic logic unit, and this should have certain peripherals or IO. That's all. So this whole thing makes a processor. So when I'm talking about 8-bit processor, so I have few standards like 8-bit, 16-bit, 32-bit. So I will focus on around this. 8-bit means I will do simple control action, on off control kind of thing, not much processing, not much precision. So I am going to use 8-bit controller, and then in this 8-bit controller, I shall try to implement a digital filter. That is my aim. All right. So let's learn a quickly 8-bit processor. So can you tell me what are the different processors available? Kariyadu Bansi Krishna. Kariyadu Bansi Krishna.
Yes, sir.
Tell me some processor names, you know. In your cell phone, what is the processor?
It's Snapdragon.
Snapdragon. Qualcomm Snapdragon?
Yes, sir.
Qualcomm Snapdragon. What is the bit size?
I'm not sure, sir. Some 832.
Please find out the architecture of Qualcomm Snapdragon processor. Yeah. Okay, tell me one more processor. In your laptop, what processors you have? You got an Apple laptop or you got this Windows laptop?
Windows laptops.
Windows laptop. Tell me the processor chipset there.
So it's Intel.
Intel or clone processors, right?
Intel. Yes.
So similarly, Apple there is M7, M3, M5 processor. So there are different processors. Similarly, their architecture is more or less same, but the VLSI is entirely different. So the VLSI decides the processor is like a big city, New York City, or maybe much more than that. Huge number of circuits, and they are so complicated and they are connected in so different fashion that you have to have lots of power management issues to control the heat at the same time, maintain the speed. So we'll talk about it later, but let's try to learn this Atmega 32 processor. Okay, any questions now? I have almost taught about over 40 minutes, so let's have some questions. So you have to know what is a processor or microcontroller. You have to know lots of sensors, actuators. You have to know lots of mixed signal ICs, simple analog ICs, analog and digital ICs. Then coding language. So here I will limit our coding language to assembly language and to some extent to C. Then in part 2 we'll switch to Python. Okay, so these are the languages. We'll keep our and some libraries, software libraries, where you have common subroutines. You don't have to write all these subroutines. So to master this or to get started, microcontrollers, so sensors, actuators, mixed signal ICs, analog digital ICs, coding language like assembly, C, and software libraries, Python. So we'll focus our knowledge on these things. We'll try to first you have to learn this, let's learn this, then you learn each one of them separately. Okay, any questions now? You have no questions? Okay, so let's get started. So I am going to tell you about this particular chip. I will directly refer to the data sheet. So you can see this chip. Ifra Asif Hassan, are you there? Ifra Asif Hassan. Please remove this guy from the meeting and remember this his name. Put a mark on this. Harsh Singh, are you there in the meeting? Are you there? Harsh Singh?
Yes, sir.
Okay, Harsh Singh, have you purchased these boards from the internet?
Yes, sir.
So what is the chip number in your Uno board?
Like, sir, 328p.
Yes, so this is the one. This particular chip will be there. You can see. So you have to understand what this. So this is 8-bit AVR company microcontroller with 32 kilobytes in system programmable flash. Programmable flash means when you write a code in the microcontroller, you can write on this flash memory. It will not be deleted. It will be there. When you switch on the processor, so whenever there is a processor, it is a programmable device. What is a programmable device? That means you can write streams of digital streams of data, which is called code. So these codes will be in the program memory. Whenever you reset this microcontroller, it will start decoding the codes and start executing. Okay, so we'll talk about it a little bit more. So this is having 32 kilobytes of in system programmable flash. All right. So so this is called advanced RISC architecture. The RISC full form of RISC architecture. Let me give you some light. RISC means reduced instruction set architecture. RISC architecture. Okay. Reduced instruction set computer, you can say. So the number of instructions decide the architecture. So instructions decides the architecture. How? Because this is basically a digital circuit. So one instructions of the other, they get processed in that by this digital circuit has a control and decode unit, which is called an instruction decoding unit. So this decoding unit is responsible for reading one. So the data instruction like data resides in program memory. So this code goes to the decoding unit. So after decoding, there is a lot of timing signal generated. And this timing signal makes data transfer, execution, addition, subtraction, etc. So one after the one instructions they execute and that leads to a program flow. So this reduced instruction means the instruction decoding unit is very, very simple. So therefore the processor is fast That means the instructions are simple. You can almost do execution in one clock cycle. All these digital circuits, they run with the help of a clock. There is a master clock. This clock runs, and because of this clock, there is execution. That means every time there is a sequential. These are sequential circuits. The sequential circuit goes on evolving. Is it clear to all of you? Gurjot Singh.
Yes, sir.
Gurjot Singh, what do you understand by the sequential logic? तुमने काउंटर पढ़ा नहीं क्या? काउंटर फ्लिप फ्लॉप काउंटर पढ़ा? Yes, so it is a sequential logic, one after the other. With the clock pulse, the data gets transformed from input to output, output to input, and there is a counting. Things are like, so there is a transformation. If X is the data now, with a clock cycle, the X gets transformed. Is it not?
Yes, sir.
If there are two registers, you can add them, subtract them. So this is called sequential logic. This happens with synchronizing with the clock. So therefore, there is a master clock, okay, in the whole processor chain. Is it clear? Okay.
Yes, sir.
Gurujot, have you brought the circuits? Whatever is was specified. Have you received your circuits from net? Ordered the circuit and got it or not?
Yes, sir. It's delivered, not delivered yet.
Okay, please try to get them as quickly as possible. So these are, so for this Atmega 32328, there are 131 instructions. The number of instructions decides the instruction decoding unit. So there are about 131 instructions. And these instructions are executed in different registers. So there is one is instruction decoding unit, and there are instruction register. Then the data resides in different registers. So there are 32 into 8-bit general purpose registers, GPRs. Okay. And the instructions per second is 16 million MIPs, which occurs at 16 megahertz. That means almost one instructions per 1 microseconds, maybe 1 by 16th of a microsecond. So GPR stands for general purpose registers. Right? So there is 32 kilobytes of self-programmable flash memory, 1 kilobytes of EEPROM, that is electrically erasable read-only memory. We'll talk about it. 2 kilobytes of RAM, which is data RAM, basically static RAM, SRAM. We'll talk about it. All right. So apart from that, so let me show you the package of this IC. You can understand. That will be easier for you. Let me show the package, IC package to you, how it looks like. So this particular chip has an architecture, also signals. So this is a specific IC packaging, as you can see. You must have seen several packages, so this is one of the packages. You can see this is the IC package. This is called TQFE, thin quad flat package, TQFE. That means there are IC leads which are coming out on the periphery. So similarly, there is DIP, dual inline package, DIP. There will be ball grid array. That means the IC chips will come out everywhere. If you look at your laptop or desktop computer, the chip which you have got, it will be ball grid array. But this is quad flat package. That means on the periphery only the IC is numbered. From this bent 1, 2, 3, 4, 5, 6, 7, 8 like that, you number these ICs. And each IC chip, IC pin has several functions. We'll talk about these functions like ground, VCC, then the port pins PD1, then there is this crystal oscillator, interrupt, etc. So they are multiplexed. One particular pin can carry several signals at different purposes, by different context. So these are multiplex signals. So these are called signals of the processor. Signals. Okay. So there is, you have to understand the signals, also the internal architecture. Then you have good idea about the processor. After that, you have to understand the assembly code and then the different peripherals. So that can make you quickly learn the processor. So I'll show you the internal architecture of this so that you can have a better idea. So this is the signal. I'll show you the internal architecture. Please note this internal architecture. Of course, you will have a manual to see it, but once I am teaching, it will be easier for you to capture. So can you see this? Is it visible to all of you? So there is a CPU. This CPU has a generic architecture. We will go to this CPU. In addition to CPU, there are lots of peripherals. So the peripherals, you know, forget about CPU. CPU, I will come back again. So if you look at the peripherals, so one is this static RAM, you can see SRAM, then program memory, flash memory, then there is a oscillator circuit, then there is another flash memory EEPROM, electrically erasable program, then there is timer counter, TC means timer counter, A to D converter, then there is watchdog unit, then analog comparator, then there is two-wire interface serial communication, and there are ports. Then there is a USART. USART is for universal serial synchronous asynchronous receiver transmitter, another serial interface. Then there are three different ports: port C, port B, port D here. Then there is other ports also, port A, port B. So in the other upper cycle you can find watchdog timer. We'll talk about it. Watchdog oscillator. Then this debug wire. Then programmable logic. So these are all together connected to a primary CPU, which is called the AVR CPU. So let me see the AVR CPU, and these are the peripherals. CPU and peripherals together on the same chip, same substrate. Okay. So let me just show you the CPU architecture, AVR CPU, how this CPU looks like. So look at this CPU. This CPU architecture is a very generic architecture. If you want, you should note down also, because in your note, though you'll have several opportunity to visit this particular lecture, but I would urge you to. It has an 8-bit arithmetic logic unit. This is the one, 8-bit ALU. This one, 8-bit arithmetic logic, which is very closely associated with 32x8 GPRs, general purpose register. That means all the computations that take place here. Then it is connected to the indirect addressing to the data, static RAM, and it is also connected to the code. So this program counter, this is flash program. Program counter is a register which basically keeps the address of the current address of the program. So there is a status and control register. Every processor with ALU, whenever there is a operation, arithmetic logic operation, this affects a particular set of flags which are called status and control. And there is an instruction register which is connected to the program memory. The instruction register carries one instruction which is coming from the address of the program memory. Then it decodes. After decoding, it generates timing and control signal to the arithmetic logic unit and the 32x8 GPR, general purpose registers. Then there is computation. So this computation goes on and the program code is getting one after the one. So this is called sequentially logic, which is a typical von Neumann architecture. which is sequential execution. Your brain is not von Neumann architecture, but this architecture one after the other. The flash memory, the program flash memory has the instruction one after the other. The program counter keeps track of the instructions, so it is fetched or gotten one by one into the instruction register and decoding unit. Then it generates timing and control signal. Apart from that, there are different peripherals, as you can see here. For example, interrupt. Interrupt is one of the major unit of a processor. Remember, interrupt and exception handling. We'll talk about it. Then serial port interface, SPI. Watchdog timer. We'll talk about it. Analog comparator. IO module 1, 2, 3, 4. These are digital IO modules, and there are different IO lines. So this is a data bus which is 8 bits, and there is a program bus here. So this is the typical AVR processor, and which is integrated with other peripherals, as you can see. So this whole thing, this AVR module along with the peripherals here makes the microcontroller Atmega 328. Is that clear to you? I should seek some questions right now. Okay, Yaduvanshi Krishna, please ask one question. What you have understood? Because I have quickly covered the architecture of your Atmega 32. You have to refer to this note, and I have already uploaded that into this. I can upload again. Yaduvanshi Krishna, please answer.
As of now, I don't have any questions, sir. Like, I'll refer to the book once and I will ask you if any in the next class.
Let me ask you one question. So this arithmetic logic unit is closely associated with what? Very closely connected to what? Tightly coupled to what? Pankaj Kumar Mina, are you there? Pankaj Mina. Pankaj Mina.
Yes, sir.
Tell me, this arithmetic logic unit does what? What is the job of this ALE?
Yes, sir.
What does it do?
Can you repeat the question?
Can you, from the picture, you tell me where it is connected? There are two arrows. It is connected to where? On the upper side?
Status and control and interrupt unit.
No. You check it. 32x8 general purpose registers. Right? Can you see?
It's connected to data SRAM from the
downside, but directly it is coupled to what?
Instruction register.
GPRs, right? General purpose registers. So these general purpose registers has got data. So ALU manipulates with the data. AL means arithmetic and logical operation. Tell me one logical operation.
Sir, XOR.
XOR. Comparing two registers, one is greater than the other or not. That is a logical operation.
Yes.
Okay. Arithmetic, adding, subtracting, multiplying. So all this is done by the arithmetic logic unit in cohort with these registers. Okay, general purpose registers. So there are commands for it, right? Okay, Pantunuru Krishna Rishita, Patnuru Rishita. Are you there?
Yes, sir.
Okay. So can you tell me? So there is this data SRAM. What do you mean by data SRAM? SRAM stands for static RAM.
Yes,
and
sir.
it holds data. So this data is actually, this data is responsible for, it is not code, it is data. It is different from code. So if data is different from code, where does code reside? Rishita, tell me where does the code is coming in the form of binary patterns, 8-bit patterns, one after the other. So where does it reside? I don't know. Attentive. Rahul Ranjan, please tell. Rahul Ranjan.
Yes, sir.
Tell me, where does this code reside? Code. Code are small coding, small code unit, 8-bit codes. They are also put sequentially and where it's stored somewhere. Where is it stored? Attention though, attention. Flash program memory, I told you na. This flash program is where the code is also written. When you are writing a code, how do you write? You are writing codes in the form of assembly language or binary codes. So they are also like data. This is a program. This is not data but program, but it looks like data. So the flash memory holds the code. So code is separate, data is separate. Are you getting my point?
Yes, sir.
Okay. Okay, Nanda Kishore, you answer my question. Nanda Kishore. Hey, Nanda Kishore, R. Nanda Kishore. R. Nanda Kishore. Pooja, you please mark this guy. Those people who have marked, actually, you please make a separate note and send it to me. R. Nanda Kishore, I have removed from meeting. Samar Pratap Singh. Samar Pratap Singh. Please remove him. Saraf Parth Brikrant.
Yes, sir.
Tell me, what is the job of this program counter? Where is program counter? Can you see the program counter? Name of the program counter?
Yes, sir. It is connected to flash program memory and data SRAM.
Yes. So this keeps tracks of the code, because whenever you are writing a code, you have to also write from an address. So this address location, address is a 16-bit address. So this 16 we will know about each of them. Don't worry about it. Okay. Don't get scared of learning the processor so quickly, because I'm throwing many things which you might be a little bit awkward for you. But this awkward feeling is good, because you have to quickly learn something. Means I will drive you into regions where is a lot of feeling of awkwardness. Otherwise you cannot. So program counter is the one. It's a register basically. It's a 8-bit, 16-bit register which keeps tracks of the code. So that is the program counter. Okay. Okay. Let's go to somebody like Gursim. Okay. Dhanush Kumar Reddy. Are you there? Dhanush Kumar Reddy. Gujula Dhanush Kumar Reddy.
Yes, sir.
Okay.
Yes, sir.
Tell me status and control. What does it status and what does the status and control indicate? I know that you cannot answer this very nicely, but whatever comes to your mind, it is fine.
So take the starting of the program or something like that.
Status means whenever there is an execution of, for example, a arithmetic operation, a logical operation. So there are certain flags, like there is result maybe 0, negative, positive, overflow. So all these things will be indicated on status and control. All right. You can use also bits of the particular status control register to change the mode of operation of the processor. Is that clear?
Yes, sir.
Okay. I think we are good. So we have learned many things about this particular Atmega 328P. It appears that it has got 32-bit general purpose register. So what is a register? Register basically temporary memory, 8-bit memory. So there are 32 of them. 1, 2, 3, 4, 5, 6, 7, 8, 32 of them. So they are closely connected to the arithmetic logic unit. So that is part 1 of this whole thing. This one. Okay. This one. Then there is a program, a codes. The codes are written in the flash memory. Somehow we'll talk about it. This code comes to the instruction decoder, and instruction decoder makes timing and control signal, by means of which the data from the data SRAM comes to the registers. There is manipulation of data. Then further programming is occurring. The program counter is responsible for keeping track of the program, and the status and control register will reflect the status of the result. Is that clear? This much is clear, right? Right or wrong? Harsh Singh.
Yes, sir.
Yes. All right. So let's now
Yes,
get
sir.
some of the signals.
Sir?
Yes, please tell me.
So what does data SRAM contain?
Data SRAM contains data. For example, if you want to have data, it is not code, it is data. So you can, this data SRAM can get data from the, for example, A to D converter. You can get data to the data SRAM. You can get data through from the communication unit like SPI, etc. So this connect. This is not instruction but data. Okay, we will come to know about it. There will be a lot of uncomfortable things, but we will come to know about it. Don't worry about it, because we are trying to learn this processor as quickly as possible. Okay, so let's see what else are there. So whatever I'm saying, please be careful. This you will not learn now, but eventually. So there are peripherals. What do you mean by peripherals? So this processor has certain peripherals. So one of the major peripheral is called the timer and counters. So every processor has a programmable timer most of the time. So they are required to generate timing pulses, which can be programmed. That means you can change the timing pulses. So timer and counter, they are called programmable timers. That means by changing certain bit pattern, you can change the timer and counter. You know counters like 8-bit counter, 16-bit counter, but if you can change the count and change the timing pulses by way of programming, so that is wonderful. So there are certain timer and counter, both 8-bit as well as 16-bit. So they are required for event registration and trapping. Event trapping, event detection. That means if there is something wrong, you know, if there is something is wrong in a particular, let's say the liquid level in a particular controller is high, liquid is high. So it will trigger one switch, so that switch will interrupt it, and then the timer will start. If the liquid level doesn't go below something in the different time, then there is a different control action. So these are called event marking and event trapping. So timers and counters are required for marking the events, counting the events, and also trapping the events. Remember this. We'll come back to this again. So we have 8-bit counters and 16-bit counter and 2 8-bit counters are there. Then there are PWM channels, six PWM. What is PWM? Pulse width modulation. Channels. So what is pulse width modulation? Why it is required? Anybody knows why PWM is required? Pulse width modulation. Tell me. Anybody who knows?
Yes, sir. So pulse width modulation is basically modulating the duty ratio of the digital wave that we have. So for example, if I get an analog signal from say 0 to 10 to represent it into a digital output, what I can do is I can vary the duty ratio of the digital waveform, like modulate the digital pulse such that the duty ratio is related to the analog input, so that from the duty ratio I can analog it.
Absolutely right. By modulating the duty ratio, I apply a simple filter to generate different analog values. Is it not? That is number one. Number two, this is required for different purpose. One is this audio, PWM audio. All of you in the class, please note down this. What do you mean by this PWM audio? Pooja, please create this homework. That means if I want to create an audio signal, analog audio signal, I can do it from the digital signal by proper pulse width modulation. All right. So these PWM channels are required, and these PWM channels are also sometimes required for generating very good sinusoids, very good analog waveforms. All right. So I think you are right, absolutely right. But just be more specific about these PWM audio channels. All right. So this is very important. Pulse width modulated audio channels. Then there is this US temperature measurement is also there. There is 8-channel 10-bit ADC. There are 8-channel 10-bit A to D converters. 8-channel. Okay. A to D converter. Then there is communication channel. One is called USART. This is called Universal Synchronous Asynchronous Receiver and Transmitter. So then there is this SPI. SPI stands for Serial Port Interface. So these are communication protocols. Communication protocols means there are communication standards with hardware and software both. Then there is this I2C or IC to IC serial communication. And there is this interrupt. And there are different modes, special microcontroller. So these are some of the peripherals. So what are the peripherals? Let's start with the first thing. What is so this particular Atmega 328P. This has got, it's an 8-bit AVR microcontroller. It has got 32 kilobytes of programmable flash. That means it can have 32 kilobytes of code which it can take. It has a RISC architecture. There are 131 instructions, arithmetic logic unit very closely coupled with 32x8 general purpose working registers. Then it has got a flash memory which is 32 kilobytes. There is a static RAM or data RAM which is 2 kilobytes. And there is a EEPROM, electrically erasable programmable read-only memory. This is also like a flash memory, 1 kilobytes. Okay, so these are all together. Then plus there are peripherals. These peripherals are 2 8-bit counters, 1 16-bit counter. Then there are 6 PWM channels. Then 10-bit ADC, 8 channels of them. Then there is a USART, that is a serial port called USRT. Another serial port SPI. Another serial port is I2C. Then there is watchdog timer, analog comparators, interrupts, etc., etc. So that makes the peripheral and the main part of the microcontroller. Is that clear? Now please ask some questions before I move to the next. Acha, Mumidi Hemant, are you there? Mumidi Hemant?
Yes, sir.
You tell me what is this SPI?
Serial port interface.
What does it do? Just you guess, there is nothing to worry. I know you are doing it for the first time, so definitely. So serial communication is required or not? It is required. Why serial communication is required? Suppose I have two 8-bit microcontrollers. Why I want to serially connect them? It can be connected in parallel. Umidi?
Yes.
What is the advantage of a serial communication? Tell me. Suppose your friend is sitting in the other room, you are here, there is a wall. You want to send him apples. How you will send? Suppose you want to send 8 apples at a time or one after the other 8 apples?
All apples at a time.
One after the time, right? Because if you increase to 8 apples, then you need 8 channels, 8 hands to catch. So therefore, if you beat a drum, send it. That means by clock. Clock means drum. 1 drum, 2 drum, 3 drum. Keep on sending, he will catch at the other end. So when you sound the drum, this becomes a clock. This is called a synchronous serial transmission. So by sending apple from this room to other room by help of drum beating is synchronous. But suppose you don't have a drum, what are you going to do? You have 8 apples you want to send, so you just first you throw 1 or 2 stones, which will hit him and he'll be awake. Then you send apples. So this is like start beat, sending a start beat, then he will get awake, then you send the apple. So this is asynchronous. So this UCRT is universal synchronous and asynchronous transmitter. SPI serial port interface is basically there is a clock, you will find. Okay, so there is synchronous transmission. Similarly, this I2C is there, IC to IC. So these are different serial communication standards which you learn. Can you learn a very famous serial communication standard used in automotives? Obil Shetty Hanisa, please do it. Obil Shetty Hanisa, tell me one serial communication which is very famous in automotive. अरे तुम कुछ पढ़ो, मैगजीन नहीं पढ़ते हो, अपने आप को थोड़ा टेक्निकली हैवी रखना है. CAN bus, CAN bus, have you heard? How many of you have heard about CAN bus? Control area network. CAN stands for control area network. CAN, please read about CAN bus, all of you. CAN bus architecture, this is used in automotives, aeroplanes. Okay, so this connects one automotive, typical automotive, how many processors are there? Hanisa? Mercedes C class, suppose you want to buy, how many processors will be there? Approximately, Hanisa, I told last class, about 50-100 processors will be there. Each processor has to talk to the other processor. Engine control unit, airbag control unit, anti-lock brake unit, entertainment, climate control, seat control, power window, power steering. There are so many processors, they control each one of them. So they have to talk to each other. They have to communicate with each other. So they have to communicate in a particular fashion. So this communication is generally by CAN bus architecture. All right, control area network.
Okay, sir.
Another serial communication. Let's find out from Pranav Batsal. Pranav Batsal और एक serial communication का standard बोलो. Pranav Batsal, जो very common है, तुम्हारा lab में भी है, laptop में. Pranav Batsal, are you there? अरे क्या आदमी है, उसको निकालो. Pranav Batsal को red mark दो, उसको निकाल दिया मैं. अच्छा, Joy Sai Krishnan. You tell me one more serial communication standard, very commonly used.
Sir, Ethernet.
Okay, Ethernet is also somewhat serial, but any serial which is very common to you. You use it all the time. USB. Universal serial bus. How many wires are there in a USB, typical USB? देखा है, खोल के आज के दो. One is D plus, D minus, then voltage supply and ground, earth. D plus, D minus for what? D plus is positive data, D minus is negative data. This is called differential transmission. So you are aware of all differential transmission?
No, sir.
Arundhati Naskar? Yes, are you there?
Yes, sir.
Yes, tell me a differential transmission. If you want to send a signal from one board to another board, how many wires you need? Suppose you are speaking, you want to send your speech signal from one board to another board. How many wires you need?
One, because like two, because like there will
one wire. Just one single strand wire will do, or what?
That two will do.
2 wires. So if it is a 2 wires, then this is signal and ground. But generally people use 3 wires, signal plus, signal minus, and ground. So this is called differential transmission. USB is basically differential transmission, D plus, D minus, ground. Okay, so all of you please get aware of differential transmission, all of you. Differential transmission. So USB is one of the serial communication standards. Okay. Anything else? Tell me some more serial communication standards. There are lots more actually. Bluetooth. These are all serial communication standards. Then you will go to networking. Serial communication standard when becomes complex, there are lots of layers, software and hardware layers. So this becomes a complete protocol. For example, Ethernet, Wi-Fi. So these are all different protocols. So anyhow, so we'll catch up with them. So now let's now discuss what are the different signals. So one of the most important registers in that with the status register, which is called status register. So the status register has got different flags. For example, this AVR status register had got 8 flags. So let me just name these 8 flags. The status register is very important. So let me just tell you these flags. So you can see the flags here: I, T, H, S, V, N, Z, C. So I is the bit 7, which tells global interrupt enable. That means if you disable or enable this, so interrupts are disabled. What is interrupt? Interrupt means if the processor is executing the code one after the other sequentially, as I said, but sometimes something is wrong. So if there is an interrupt, there are interrupt wires. If you make it high or low, so there is a transition. This transition is registered as an interrupt. The moment there is interrupt, the program will be suspended and it will go to something known as interrupt service subroutine. You can globally enable this interrupt or disable it by bit 7. By setting or resetting the bit 7, R/W means read write. Both you can read and write here. These are R/W, read write signals. So you can enable this global interrupt, you can also disable it. Similarly, the bit 6 is T bit. So this is called bit load bit or bit store bit. So this can be used with something called bit load instruction. That means you can change a bit of a particular register by writing a bit here and then using this bit load instruction. Then bit 5 is called half carry. If the result of a particular 8-bit operation, there is an auxiliary carry which is generated at 3rd bit to 4th bit, then this half carry is activated, H. Then S for sign bit. Sign bit, if the result of a operation is negative, then the sign bit is activated. Similarly, there is overflow. V is the overflow and N is for register negative. If the result is negative or not. Then the Z is for 0, C for carry. So these are different status registers. So by means of the status register, that means it is reflecting the nature of the result. If there is negative sign, overflow, 0, or there is a carry or half carry, it can be used to enable and disable interrupts. So this is called the status register of AVR, SREG. And the general purpose registers I have said, there are 32 general purpose registers. And the some of the specific registers can be used in pairs. For example, there is a X register, which is 26, 27, XY register. They can be used together to become a 32-bit register. Then there is a sorry, X low, X high, Y low, Y high, and Z low, J high. These 3 pairs of registers can be used as 32-bit register at a time. So these are general purpose registers. So apart from the general purpose registers, there is a program counter. The program counter's job is to keep track of the code. That means when you want to reset the processor, PC becomes 0, 0, 0, 0. That means all the program counter contains at 0, 0, 0, 0. 0, 0, 0 means, so the flash memory starts from 0, 0, 0. The code will be gotten from this first memory location and decoded and executed. So you start writing the code from 0, 0, 0 location. Apart from the program counter, there is something called a stack pointer. We'll talk about stack pointer. So stack is a particular memory where there is a push and pop instruction. That means you can push onto the top and pop from the top. The stack is generally used for calling subroutines. When you call a subroutine, the present address is pushed into the stack. When you come back to the subroutine, then the address is popped back. So the operation with stack is, so there is something called a stack in the memory, which is little unconventional. So the operations are push and pop, and the stack pointer points to the top of the stack. So if this is the stack, the top of the stack will have an address which will be indicated by the stack pointer. And it is mainly used for calling subroutines and functions. All right. So I think we have covered the major ground. Now we shall discuss tomorrow next class. That is, you guys can go through the instructions, execution and assembly language code. So I think you can directly download the AVR assembly language programming guide. So I shall AVR assembly language programming guide I will share by net. You start coding. Okay. Don't wait for me. Tomorrow again on Tuesday there will be a further demo on the hardware. So then I shall continue with this assembly language coding on Monday. Okay, so but you don't wait for it. You just try to learn and catch it up. If you have any questions, you can answer. You can ask questions now. We have got 10 minutes left. Aviral Singh, do you have any questions?
No, sir.
All right. Mohit. Mohit.
Yes, sir.
Do you have any questions?
Sir, one question is that the C language is easier than assembly language, but so why we use assembly language?
Assembly language you can, if you want to write virus, for example, best to write in assembly language. You can manipulate all the resources of the processor. In C language, the assembly language conversion has to be there. Eventually, the machine will understand assembly or binary codes. So the more you write on machine, the more you can exploit the machine. That means the processor. So C language will create some very unnecessary overheads, etc. But eventually, to quickly develop a code, you have to write in C language. But to do very minutest level, register level manipulation of the data, better to write in assembly.
Okay.
Right. Hemashri, N. Hemashri.
Yes, sir.
Any questions?
No, sir.
Nayan Jyoti. Nayani Jyoti.
Yes, sir.
Tell me.
Sir, no question.
Pranav Batsal. Pranav Batsal.
Yes, sir.
हाँ, क्या क्वेश्चन है पूछो?
नहीं सर.
तुमने आज क्या सीखा? तुम्हारा जब प्रोसेसर तुमने खरीदा है 8 मेगा 328 उसके बारे में. This processor has कहते हैं arithmetic logic unit, 32-bit registers, so lots of things associated with it. Peripherals.
Yes, sir.
So once you know coding, you can manipulate all the peripherals, everything together, and the processor can be executed. Okay.
Yes.
Sarab Parth Vikrant. Sarab Parth Vikrant.
Yes, sir. Yes, sir.
Tell me, what is stack pointer? What does it do?
Sir, actually it has the push and pull instructions, and it stores
stack is a memory area where you store by push and pop instruction. This is required to when you do subroutine call. We'll talk about it. And a stack pointer points to the top of the stack. Stack pointer is a register, okay, which gives the address.
Yes, sir.
Shivam Pratap Singh.
Yes, sir.
What is differential transmission of data?
Differential transmission. So you said to know about it before
yes,
the.
Ultimately, suppose I want to send 0.5 volt signal to one place to other. You need 2 wires. Why need 3 wires? For differential transmission, I will have 3 wires. How do you generate these 3 wires? you have one signal which is oscillating between 0 to 5 volts. So one end you send, another end. What is the third wire? How will you send that third wire? Think about it, okay? Think about it. Command mode rejection, okay, all these things. Bishesh Anand, are you there, Bishesh Anand?
Yes, sir.
Tell me, what did you learn in this class?
Sir, I learned about AVR microcontroller, its architecture, and a little bit on the brief about every component.
Right. So you are going to read that manual, okay?
Yeah.
So which I have shared, now also I am sharing. All of you please go through this manual. Next time there will be lots of questions, lots of discussions. Whoever is attending class, be attentive. Otherwise, once you have a black mark, you know, your grade will not be improved. If you are getting a B grade, I will not make it A. So there should be good impression. You know what happens in the grading. Generally, when you are in borderline, we increase one grade. But if you are not attending the class very insincere, so the professor will definitely not do that. Is that clear? So all the best, guys. So I am sharing this data sheet. Okay. Also, I will share the assembly code. Already there is a copy already existing. I am replacing it. Then AVR assembly language programming also. I am giving one copy also. AVR assembly language. Okay, so I have uploaded this. Then I shall give you one AVR assembly language. I shall give you right time. Okay. Somewhere I will give it. So I am also uploading this document. You can, this will become handy. AVR assembly. Okay, all the best. Bye.
Thank you, sir.
Thank you, sir.